is going to look like now. So molecular formulas are not simplified. These are going to be our true formulas. Okay, so true formulas now. So that means that it could look like it can be reduced, but we leave it alone. So basically, the description kind of coming down the page here, it says, a molecular formula is the actual formula now. So that is that it shows the types of numbers of atoms found in a single molecule of the compound. For example, ethane and cyclopropane are very different substances, yet they both share the same empirical formula. The empirical formula tells you their mole ratio, but their molecular formula would be needed to tell you more about the molecule, like their properties and things. So really what's going to happen is the relationship between the molecular and empirical is described as X times your empirical equals your molecular. What that means is a ratio times your empirical gives us our molecular. So on your green page, one thing that we kind of had to correct last period was right here. I don't know why that 100 is there on your green sheet. So some people in last period kind of started scribbling it out. Otherwise, I'll go through it today after school and just kind of scribble that out. So if yours still has 100, just know you're not using the 100. But it is going to be molecular formula mass, which is usually given to you, over your empirical formula mass. That's usually one that you would have to calculate. Is going to give you some sort of a ratio. So actually, all of that's going to go away. Gives us a ratio, and then the ratio times your empirical formula subscripts is what we're going to get for a molecular formula. Okay, so I'll go through and fix your guys' green pages. All right, so looking at example 1, it says experimentation shows the formula mass of diborane to be 27.67 AMU. That is your molecular formula mass. Okay, the empirical formula is BH3, so we would have to get the empirical formula mass. All right, so what we have here, we're going to be putting our molecular formula mass, which is also known as the experimental formula. I just like it to be 2 different letters. That way you're not getting it confused on your page. Over empirical formula mass. All right, so BH3 has an empirical formula mass of this. So that's what this number is. The way that we got that was that we saw boron plus 3 hydrogens gave us 13.84 AMU. That was our empirical formula mass. This 27.67 was the molecular formula mass. That was given to you. Okay? When we divide them, we got the number 2. You should be getting extremely, extremely close to a whole number. If you do not, then it's probably not correct. All right? This one should be very, very obvious to a whole number. Okay? And then once we have that, we're going to multiply it by the subscripts in order to get our molecular formula like you see right there. Okay? So, example 2 says the empirical formula of a compound was found to be P2O5. Okay? So that means that our empirical formula mass is equal to 2 times phosphorus, which is 30.97, plus 5 times oxygen, 16.00. So that mass should come out to be 141.94. Okay, so that's my empirical formula mass. According to the problem, it says experimentation shows that the formula mass is that. So our molecular formula mass is 283.89. All right, so with those two, it's always going to be big number divided by small number on this one. All right, so molecular formula over empirical formula. So 283.89 divided by that 141.94. When you divide that in your calculator, you're going to get 2.00000, blah, 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 blah. So it's 2. The way we use it is we have our empirical formula, P2O5. We're going to multiply 2 by that. So that gives us P4O10. And that's it. So in my opinion, this one is a little bit easier because I would say the most challenging thing that you have to do is figure out your empirical formula math sometimes. Okay? But other than that, those are the two formula things that we're going to be working with.